Hello, my name is Chris Harris and I'm from Allery Chemistry, and in this video we're going to be looking at the CIE, which is the Cambridge International qualification, topic 1, atomic structure, and obviously in this video we're going to look at the content in the atomic structure topic for topic 1. Everything you see on here is obviously in PowerPoint form, and they are available to purchase from my test shop that I've got. If you click on the link in the description box below, you'll be able to have a look at them there. They're great value for money, so please go and have a look. I've kind of bunched these ones up, topic 1, with some other topics as well, which fall into the physical chemistry section, so you don't just get topic 1, you get some of the other topics as well. So go and have a look on there, there's loads of stuff on there. But the purpose of this video really is to talk through some of the key points within the CIE topic in particular, the CIE specification in particular. So it's really there for revision, so you can pick up on it, and hopefully it should make it a little bit easier to understand. So if we start with, hopefully you should be able to see my cursor. I'll kind of move things around on the cursor here so you can see what I'm talking about. So this topic starts off with subatomic particles, and obviously as it suggests, or the topic suggests, we're looking at the structure of the atom, and we're looking at the variations of atoms, such as isotopes and a little bit of free radical stuff, ions, and looking at trends and things like that. So there's a lot of this in this topic here. But the first thing I suppose we need to look at is what is actually an atom made from. And I suppose in this case, an atom is made up of subatomic particles, and these are called protons, neutrons, and electrons. And so protons and neutrons are the only ones to actually have any form of significant mass. Protons do have a positive charge, electrons are negatively charged, and neutrons don't have a charge at all, so neutron neutral. Now what they want you to do is to try and how do we know that these particles exist? And one of the methods we can use is by using electronic plates and trying to separate out the different components of it. But and we'll show a diagram of that in a moment. But if you look at an atom, now the nucleus of an atom, which is obviously in the middle of the atom, is positively charged. It contains protons and neutrons in there, and you've got these negatively charged electrons. These orbit the nucleus, so they kind of spin around. Now, most of an atom is just empty space, actually. You know, most of the mass, the majority of the mass, the vast majority of the mass, should I say, really is in the nucleus, which is the smallest part of an overall atom. But like I say, we can demonstrate the kind of composition of an atom by passing it through an electric field. And so when we pass these particles through an electric field, we can state the following facts about these. So you'll see on the diagram there, you see you've got a positive plate, which is here, and you've got a negative plate here, and you've got electrons, neutrons, and protons. These are the kind of main constituents of an atom. So what we can deduce from this is that electrons bend the most, as they're the lightest subatomic particle. So you can see that's bent quite significantly compared to the neutron and the proton down there. We can say that electrons do bend towards the positive plate because they're negatively charged and opposites attract, of course. And then the third point we can say is that neutrons are not affected by the electric field. They don't actually have a charge at all, so they just go straight through, so they're unaffected. And the fourth point is that protons have a positive charge and bend towards the negative plate as they attract. Again, opposites attract. So these are the key points that we can effectively deduce from the outcome of this experiment, which proves that an atom is made up of these three main subatomic particles. Okay, so ions and isotopes. So we need to kind of look at the different kind of forms, I suppose, of some of these particles that exist in chemistry. So this is quite fundamental, really, and you might have seen bits and pieces of this at GCSE, perhaps, more than likely. So let's start with ions first. So ions have a different number of electrons and protons. So, for example, if we look at negative ions, so oxygen as an element has 6 electrons in its outer shell, what we'll call its valence shell. But it can gain 2 electrons to form a full shell of electrons, which is more stable than if it had 6 on the outer shell. So that's why oxygen, for example, forms a 2 minus ion, so O2 minus. Now, if we're looking here, we need to look at the number of protons in oxygen, and the number of protons is 8. The number of neutrons is 8, and the number of electrons in the ion is 10. Now, normally, the atomic version of oxygen has 8 electrons as well. It gains the 2 electrons to form O2 minus, and so therefore the overall charge is 2 minus, as you can see on there. So positive ions is kind of the other way. So these are normally group 1s and group 2s, which we'll come on to in a moment. But just to give you an example, sodium, Na+, this has lost an electron to gain a full, or to kind of achieve a full shell, a full valence electron. So that's the outer shell of electrons. And this is obviously forms a much more stable species. So this is an Na+ ion. Now, the number of protons in sodium is 11, the number of neutrons is 12, and the number of electrons is 10. So, remember, neutrons don't have a charge, so the protons obviously have a the positive charge, so that's plus 11. The electrons is minus 10, so the overall charge here is plus 1. So this is obviously the charge of sodium, and that's basically what an ion is. And obviously the reactivities of these can change, as you'll see later on when you do ionic bonding, for example, and we'll look at the trends of ions as well throughout various different periods and groups. So we'll look at that as well a little bit later on in this video. So, isotopes, on the other hand, are a little bit different, and these are elements where they have the same number of protons, but they have a different number of neutrons. Okay, so here we're not changing the number of electrons in an atom, we're not adding electrons or taking electrons away. This is unchanged. What we're saying is this is an element which just has a slightly different number of neutrons. This is quite common. A lot of elements in the periodic table that you see on there do have various different isotopes of the same element. So a classic example, which you probably might have seen quite often, is carbon. Carbon has 3 main types of isotopes here. So this is all carbon, so the element of carbon is the same. The bottom number, which is the proton number, this is obviously 6 for all of these. But the actual mass number, so the number here at the top here, so the bigger number, tells you the number of protons and neutrons in an element. Now you can see this number changes, as obviously depending on which isotope we're looking at. So, for example, you can see on this one here, the first one, so this one's got 6 protons, 6 neutrons, and 6 protons in all of them, as I mentioned before. But the number of neutrons is different. So you can see here that we've got 6 neutrons in this example, 7 neutrons here, and 8 neutrons here. So we've got a different number of neutrons altogether. So this is going to be quite important. I'll come onto the radical bit in a moment. But when you're looking at isotopes, so the mass number changes. So there's a change in mass of these elements. So for example, carbon-14, which is this one, this element here, is obviously heavier than carbon-12, but the actual the element itself is still carbon because it's got the same number of protons. So the number of protons dictate what element it is, and that's really, really important. And actually, the reactions of these, all of them, are going to be the same because they have the same number of electrons in the outer shell, and it's the electrons that are exchanged in a reaction that basically dictate how an element will react. So the fact that we've got different isotopes doesn't actually change that at all. So kind of looking at, and you've seen it just pop up there. One of the things that Ed is talking about, another thing you need to be aware of, I suppose, is free radicals. You'll see this a lot more, in future topics. So it's really just to introduce it. But free radicals are represented as a dot. For example, you've got Cl dot, and that suggests that it's a radical. And basically, this is a species that has has one or more unpaired electrons. So a classic example is chlorine atom. So chlorine atom obviously has 7 electrons in its outer shell, in terms of its main structure, but one of them electrons is not paired. So effectively, it's a radical, and that's why chlorine, along with its other elements in group 7, normally go around as a pair because it's more stable for them rather than to exist as a radical. So you might see that later on. In fact, you definitely will see that. Not you might, you definitely will. So yeah, so just to make sure you're kind of aware of that. Okay, so let's look at some electron configurations. Now, you might have seen some of this again at GCSE. It depends on obviously which syllabus you followed, whether it's the internationals or whether it isn't. But effectively, shells, you know what a shell is. When we look at shells, you have shells of electrons around a nucleus. Now, these shells are actually split into subshells, and you have 4 different types of subshells. Not all atoms will have all of these. Some of them will have all of them, some of them won't. It depends on what element it is. But effectively, you need to know what the 4 subshells are. So your first one is the S subshell. This one has 1 orbital and it can hold 2 electrons in there. The P subshell has 3 orbitals and can hold 6 electrons. So you're probably getting the pattern here that each subshell can hold 2 electrons. That's the maximum. D has 5 orbitals, and so obviously if you've got 2 electrons in 5 orbitals, that's 10 electrons in total. And the F subshell has 7 orbitals, so this can hold up to 14 electrons in total. So what we're trying to do here is that we're saying, right, okay, you do have shells and they do exist, but we're breaking them shells down a little bit further and actually broken up into kind of mini shells or subshells. That's basically what they're called. So, for example, you have subshell. Oops, let me just go back, sorry. So let's say you've got shell, the first shell, for example, will have what we call a 1s subshell, and I will get that out eventually. And that has the number of electrons that can be held in there is 2 electrons. So the second shell in an atom, so if an atom has 2 shells of electrons that you'd be familiar with, then it will have a 2s subshell. So basically the 2 tells you that it's the second shell. The S obviously tells you the suborbital, but you also have some P subshells in there as well. So this is the first time when you get into the P subshells. So this will have 2 electrons in the first subshell. It'll have 3 lots of 2 in the next one, so that is 8. And this is where you get your traditional kind of octet rule that you can have 8 electrons. But unfortunately, that octet rule doesn't really kind of it does exist, but the model breaks down when you get to bigger elements. And this is probably explained quite nicely in the third shell, where you have your 3s. So this is your third s shell. So you still have s orbitals, suborbitals. You have your p suborbitals, or subshells, sorry, should I say. And then you also have some d subshells as well. Now, in total, elements which have these number of shells, for example, can have 2 electrons in the s subshell. It'll have 6 electrons in the P subshell, and it'll have 10 electrons in that D subshell. So effectively, you can hold 18 electrons in the outer shell, as you may be aware of it as. And this outer shell is split up into these 3 different subshells. So hopefully that kind of explains it a little bit further, because you are going to see this a lot more, especially in this video, but you are expected to kind of get your mind into this kind of set here about the S, P, D and F subshells, rather than just talk about shells from a generic point of view. So they just want a little bit more detail at A level. Okay, so let's look at some electron blocks. Now we've looked at the different shells. We looked at the S, the P, and the D and the F shells, etc. We can actually help to kind of categorize the periodic table into them different subshells. So and the group number, as you're probably already aware, the group number relates to the number of electrons in the outer shell. Okay, so you kind of should have seen some of that GCSE. So, for example, group 2 elements have 2 electrons in the outer shell of their electrons. So these elements here, so groups 1 and 2, are also known as S block elements, because their outer shell of electron, or their kind of valent electron, sits in the S subshell, okay, or the suborbital. Now, these ones on the right-hand side, so this is group 3 to 8, these are known as p-block elements, and that's because their outermost electron will occupy, generally will occupy a p orbital, a subshell. And these ones in the middle are known as d-block elements, so that's the block in the middle. And then these ones, you might not see much of these, to be honest, but these are called f-block elements. So these are the ones that kind of sit towards the bottom of the periodic table. Okay, so let's look at these shells or subshells a little bit more. And as I mentioned before, they're also known as orbitals. And orbitals, as you may have seen in physics, if you do physics, they obviously have particular shapes. So remember, if we just go back a little bit, when we said the S subshell had one orbital, and this can hold 2 electrons maximum. Now we need to know what these things look like. So the S1 is nice and straightforward. It's just a sphere. Okay, it's spherical, has 2 electrons, and they can move anywhere within that sphere whatsoever. Okay, so this is just where do these electrons move around, and imagine it's a bit like a football. You've got electrons whizzing around inside, and they can basically exist anywhere at any one time. Now, your p subshells, they have 3 orbitals, and each orbital can hold 2 electrons, as I mentioned before, and so that means you can have a total of 6 electrons in these orbitals. Now, they're given these funny names. Don't be too put off by them. They're not called, like Simon and Susan and I don't know, Paul or something like that. So they've got these funny names, which is the first one's called a px orbital. There we are. It's to do with obviously I know obviously where the x and the y comes from. If you do maths, you'll probably see the link here. But this is called a px orbital. So that's an orbital that's on its side. The py orbital is kind of vertical, and then you've got the pz orbital, which is kind of diagonal and kind of pointing away from us. So you've got these 3 different orbitals here. Now, basically, the electron will kind of exist in any one of these lobes here. You've got 2 electrons in each one of these. Now, these are then broken down individually. In reality, obviously, they've obviously all merged together, as we'll see in a moment. But these orbitals are obviously 90 degrees to each other as well. You can see, obviously, the orientation with them. Put the lines on there. And there we are. And if you kind of merge all of them together, you have what looks, probably you might have seen some pictures of atoms that look a little bit like this. If you look at kind of diagrams on Google or something like that, then these make up the p subshell. So there's 3 p orbitals in the shape of dumbbells, and each of them can hold up to 2 electrons, and they can move obviously anywhere within that shape as well. Okay. So you've got to be aware of something called spin pairing, and this is when 2 electrons occupy one orbital. They basically spin in opposite directions, and you're going to see a diagram next, which kind of shows electrons as arrows. Yep. So very creative as chemists. But yes, you'll see this, quite often in exam papers, for example, or in your books, etc. You'll see electrons represented as an arrow because why not? It's difficult to draw an electron, it's just a spherical object probably. So yeah, so we use arrows to do that. But what you've got to be aware of is that they actually spin. One spins clockwise, the other one spins anti-clockwise if they're in the same orbital. Okay. Right, hope you're following. So this is where we're then going to kind of expand a little bit further and just look at how we can actually write what we call an electron configuration. And you might be asked to write this as well in the exam, so it's really important that you're able to do this. And I've put a little bit of a diagram up to help us here with this one. So when you write, they might say write the electron configuration for an atom, and you have to make sure you're kind of writing it in the correct way. So the first thing to notice is to look at how it can be written. So the big number, when you write any electron configuration, tells you the shell number. So this is, like I say, what we've seen at GCSE. The next letter is a little letter that tells you which subshell we're talking about. And the last one tells you the number of electrons in that subshell, which in this case is going to be 2 on this one. And then we can obviously link this to try and, because it's quite difficult to kind of get your head around it. So what we've done is kind of put the diagram on to show you what these kind of subshells look like. So Let's have a look at the electron configuration for iron. So we've put iron on there. It's a nice big element, so we can talk about loads of different kind of variations and different orbitals here. So the key number, obviously, we're going to be looking at is going to be the number of electrons in the element here. Now, in this case, it's an element, so the number of electrons equals the number of protons, which is going to be, as you can see, is going to be 26. Hopefully, you can see that on there. So we know we need 26 electrons in total, but these electrons are going to occupy different shells and different subshells, and that's really what we're going to try and write out here. Okay, so let's have a look. So the first one, obviously, we've got 1s2. Okay, so that's 2 electrons in the s subshell, and it's in shell 1. Okay, that's basically what it is. And you'll see on the diagram there, do you see this is where believe it or not, this is how we draw an electron as an arrow. And you can see the box represents the orbital, and there's 2 electrons in that box, and one is spinning one way, one is spinning the other, and that's your first one. That's 1s. It's quite low in energy, this orbital here. Okay, that one's full, so we need to add more electrons. So we're going to add 2s2. Okay, so that's the next. It's another s subshell, a little bit higher than the first one, but again, we've got 2 electrons in there spinning opposite directions. The next one is your 2p orbital. Now, this one you can hold 6 electrons in total, 2 in each orbital, and we've just seen there are 3 orbitals in total, and obviously the electrons are spinning in opposite directions, as we can see there. Okay, so 3s2, obviously we just put the next one in, and then we're just going to add another one, okay, which is your 3p6, as you can see on there. Okay, and then what gets a little bit weird is actually the 4s comes before the 3d. The 4s is slightly lower in energy than the 3d, and this is going to become significant when we look at ionisation later. Excuse me. So you can see we've obviously put the 4s in there, and then we're going to put it into the 3d orbital there. And basically, we know if we've got everything right, because the small numbers should add up to give 26. In this case, it does. So we know we've got the right amount in there. The key thing, though, to look out for is that we always fill from the lowest energy level upwards. Always. Okay, you must start the lower. You can't just start anywhere on this diagram. You've got to start from the front and fill them up as you go along. Okay, so that's quite important. And we do fill orbitals singly first, and then we pair them up. And this is because of electron repulsion. Electrons really don't want to be near each other, because they're obviously all negatively charged, and negatives don't want to be near another negative. So if they can occupy a different orbital away from another electron, then they'll do that. So, and this is why when we fill up this orbital here, they'll kind of occupy their own place first, and then only if they have to will they kind of pair up into the same orbital. So it's a bit like, to use an analogy, I don't know, it might be just me, but if you say go on a bus, for example, and you've got people who will arrive on the bus, they're probably likely to find a chair of their own, and they're just going to sit on that bus and kind of, rather than sit next to somebody else. Maybe it's for privacy, I don't know, but that's what I've noticed. That's what I've kind of observed. And it's the same with electrons. So when you've got electrons here, they will kind of prefer to kind of take their own seat individually, and only if all the seats are taken singly will they then have to sit next to somebody else if they want a seat. So it's the same with electrons as well. So a little bit of an analogy there. So just a bizarre observation that I make. Okay, so with ions, what we do is we just add or remove electrons from the highest energy level first. Now, transition metals, as we've just seen before in the periodic table, kind of behave a little bit differently, and we'll kind of look at that in the next slide. But the kind of concept is the same. Remember, we're looking at ions, we're either adding or losing electrons here. So, for example, let's look at the electron configuration for calcium 2+. Now, calcium is in group 2. It loses 2 electrons from its outer shell, so its valence shell, to form the 2+ ion, so it loses 2 electrons. Now, in this case, this is obviously the setup here for calcium 2+, which is here. So it's going to lose the 2 electrons. So there it is. Okay, so you get your 4s2, and there it drops away. And that leaves you with your electron configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so if we add up all of the numbers on there, then that should give us the total number of electrons as 18. So basically that's all we're doing. We're just removing the electrons from it, and we're going to lose it from the 4s at the top. There we are. See it disappear. And basically that is now your electron configuration. So it's fairly straightforward. It's not too taxing, hopefully. Anyway, so this is where it gets a little bit more confusing though. Okay, and this is for transition metals, can behave a little bit differently, so some of them can anyway. And the ones in particular that we need to be aware of is chromium and copper do behave a little bit differently to other transition elements. So an electron, and here's the structure here, and you can obviously see the structure there. So an electron from the 4s orbital moves into the 3d orbital, okay, to create a more stable half full or full 3D subshell, respectively. Okay, so if we look at chromium, for example, so this is if you find chromium in the periodic table, then its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Okay, it's not. Remember when we looked at this diagram here, and you can see here, normally we would fill that electron there, and then we'd fill the rest up here. With chromium, it isn't. Actually, what happens is one of the electrons, instead of it being 4s2, and you can probably see it there, instead of that, one of the electrons jumps from the s orbital and finds a vacant seat in the 3d orbital instead. And effectively, this is more stable than this configuration here. So just make sure you're kind of aware of that. That's really important. And then your transition metal ions, they behave differently too. So if we look at, for example, if we look at iron as an example, so Fe3+, okay, so let's look at the electron configuration for Fe3+. So this loses 3 electrons, okay, so because it's 3+, we lose 3 electrons. So 2 actually come from the 4s orbital, and 1 comes from the 3d orbital instead. So let's have a look. So there's our electron configuration there. So you've got 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. Okay, so this is your electron configuration. Now, if we remove 3 electrons, there we are, that's what we get. So we actually remove it from the S and then 1 from the D. So that's really important that actually we are removing from the S first, even though it's lower in energy than the D. So in other words, we're not removing them all from the D first and then the S. We actually remove from the S and then from the d orbital first. Really important, okay? So don't automatically assume for transition metals that you remove from this 3d first, clear that out, and then remove from the 4s. It always, you remove from the 4s first, then from your d orbitals, okay? So that's really important. It's quite a bit of a quirk. And obviously check your numbers, use the small numbers. This should add up to 23, which of course it should do. Okay, so there we are. We're going to remove it from there. There we are. Disappears. And there we are. Okay, and so this is your electron configuration for Fe3+. Okay, so let's look at some ionization. Obviously, we looked at a little bit there already, but we need to be aware of, I suppose, the kind of the different trends and what does ionization actually mean, and looking at energy and looking at graphs and things like this. So there's a little bit of kind of work to do here. So ionization energy, so this is effectively the minimum amount of energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. Okay, really, really important. You've got to be aware of what the energy bit is, because we're going to be talking a lot about energy here. So let's have a look. So this one here, sodium, for example, this is an equation showing the ionization of sodium. You might have seen something similar with GCSE, like I say, but just as a refresher, sodium obviously will lose an electron to form Na+, as you can see on there. First ionization energy for this is just the value of how much energy is required to do this reaction in the first place. What you'll notice is that when you lose an electron, we never put Na- electron. We always write it whereby sodium produces the electron. We always say that electron is produced in this case. Okay, so it's always plus E-. And obviously they're all in the gaseous state, because this is just the standard way in which we measure ionization energy. So always include your state symbols, and ionization obviously always requires energy. So they are always an endothermic process. And so always, in terms of your ionizations, your first ionizations, they will always have a positive value as well. You'll see a little bit more of that later on. So one of the things which kind of impacts ionization, there's a few things here, but one of the first ones is something called shielding. Okay, now shielding, as the name suggests, the shield is obviously there to protect. So if you had a shield, say as like a knight or something like that, then a shield is there to protect against something. So shielding in chemistry, this is obviously protection of an electrostatic force from the nucleus, i.e. a positive charge, to the outer electron. And how much shielding, how much protection is there from the attractive force of the outer electron that's been removed to the positive charge in the nucleus, which is trying to hold it together. Okay, so if we look at this diagram here, so the more electron shells between the positive nucleus in the middle and the outer electron that's trying to be removed from the outside will obviously have an impact. Now, the more shells there are between that and the outer shell, then the weaker the force is going to be, and so therefore it's going to be easier to pick that electron off the top there. Whereas with this diagram, there isn't as much shielding, so there's only one shell really there in between, and so therefore this atom here is going to hold on to the outer electron a little bit more tightly than this one here. So it's going to be a little bit more, it's going to require more energy to remove that electron. Okay. The other one is atomic size, which is probably a little bit easier to kind of understand. Basically, the bigger the atom, the further away the outer electrons are from the nucleus. And so therefore, obviously, the attractive force between the nucleus and the outer electron reduces or decreases, and so therefore it's easier to remove the electrons. So atoms which are just bigger than other atoms will lose its electrons much more readily. It's just much more difficult to keep a hold of that outer electron. And another example, the final one, is nuclear charge. Again, probably quite obvious, but it's basically the size of the nucleus in comparison to the number of electrons that are around there. So the more protons in the nucleus, the bigger the attraction between the nucleus and the outer electrons, and this means you're going to need more energy to remove that outer electron. Okay, so these three different parts here, so shielding, nuclear charge, and atomic size, are all factors which can impact or affect the size of the energy required to remove that electron. And seeing as though removing electrons from atoms or receiving electrons is integral to any chemical reaction, that's going to be quite important. And this dictates quite a lot of the chemical reactions that we see in chemistry. So it's actually quite important. We're just looking at this on an atomic scale, of course. So let's look at some trends, shall we? So if we look at the first one, which is looking at first ionization trends. So this is looking at the trends for the removing of just one electron, or the first electron, from an atom. Now, obviously, some of these elements, they can have loads of electrons that can be removed. But in this case, we're just going to look at the first one. So ionization energy decreases as we go down a group. Okay, so we've got elements here, which is obviously group 2 in this case. So this is beryllium, magnesium, calcium, strontium, and barium. And this is obviously showing the ionization energy of these elements as we go down that group there. So obviously, as we go down group 2, and you might want to have a periodic table in front of you to go through this. As we go down the group, the outer electrons are actually further away from the nucleus, and so therefore the attractive force is weaker, and so the energy required to remove one electron from each one of these different elements decreases, and that's pretty much what we're seeing in that graph there. Shielding obviously increases as we go down the group because we've got a lot more shells between the nucleus and the outer electron that's obviously been removed, so the energy required also decreases as well. And then obviously this data obviously provides strong evidence for shells in atoms, and this is how scientists know that there's definitely shells within atoms there, because this is obviously showing you that obviously the amount of energy required to remove an electron changes as we go down, because they must sit in shells which are which vary, I suppose, which well, they'll sit in shells that are, that vary in distance from the nucleus, and obviously the evidence here, the kind of graph shows that as well. Okay, so let's kind of spin it on its head a little bit, and let's look at successive ionization energy. So in other words, we're going to pick on one element. This poor element's going to be magnesium, and we're basically going to strip it of all of its electrons. In theory, obviously in practice it's quite difficult to do this, but in theory, what do we see here? So we're going to look at successive ionization, rather than the previous example where we looked at just taking one electron from each atom as we go down a group. We're looking at one element here. So the removal of more than one electron from the same atom is called, obviously, successive ionization, as I mentioned before. So, for example, if we look at, say, magnesium, so magnesium that's already lost an electron already, so Mg+, removing another electron from it, so basically you're successively taking electrons from it, has quite a large energy that's required, or a large amount of energy is required to do that. Okay, and obviously, hopefully this graph will kind of demonstrate that a little bit further. So what you'll see, if you look at magnesium, now remember magnesium is in group 2, okay, so it obviously has 2 electrons in an outer shell, and then all of a sudden you've then got to remove electrons from shells that are much closer to the nucleus. So what you see on this graph is a bit of a jump. You get jumps at certain points, and again, this is more evidence for shells. So if we look here, so the energy required to remove one electron is here, the second electron is here, but then when we start to want to move the third electron, remember that electron is closer to the nucleus, then you suddenly need a much greater amount of energy to remove that. And then as we carry on going all the way through this group, it kind of, you've got obviously 1, 2, 3, 4, 5, 6, 7, 8, and then when you start to take some more electrons after this is your p orbital, your s and p orbitals here, then it jumps up again because you're having to go into another shell that's much closer to the nucleus, and this shell is obviously the one that's closest to the nucleus, so there's another big jump here. So this is evidence of actually of shells, and successive ionizations kind of shows that. So obviously you've got a general increase in energy, obviously as you're removing an electron from an increasingly more positive ion. So there's that general trend, but you do have these jumps as well. So for example, as you go across this period here, remember the number of protons in the element compared to the number of electrons is obviously increasing as a ratio. So you're not increasing the number of protons remain the same, but the number of electrons is obviously reducing, and so therefore that kind of positive charge compared to the number of electrons left is quite great, and that increases the energy required to remove that. So if we just kind of look at these different sections here, so you can see obviously this is your 3s orbital, so these are the ones which are furthest away from the nucleus. Imagine the nucleus is here on this graph here. The next lot is obviously your 2p's and 2s's, as I mentioned before, and the final two at the end there is obviously the ones in the 1s orbital there. So, and we know this is obviously Mg because we are removing 12 electrons. So the exam board might give you, say, an element, for example, and they'll probably give you a graph, and they'll say, right, what element could this be? This is the successive ionizations. Really, what you're looking for is how many electrons are being removed by the, by this, how many electrons have been removed from the atom. In this case, it's going to be 12. So you look at the periodic table and see which element has 12 electrons in it. Okay? So, hopefully that kind of makes sense. And obviously this feeds into, obviously, the modern periodic table. And the periodic table is structured in that way. It's structured to kind of reflect the shells and subshells that make up the elements, obviously, that we see today. So it's really important when we're looking at the periodic table, we need to know some basic features about it. Now, some of this you might have heard of before, and this kind of builds on it a little bit more and brings in some of the A-level concepts. But elements are ordered by proton number, not mass number. Okay, really, really important. So you can see, obviously, the numbers at the top here is the proton number. That's the number of protons in the element or the atom. So obviously these groups, groups obviously the columns, which kind of go down. So we've mentioned a bit about the groups already. And obviously the elements in the same group have the same number of electrons in the outer shell. So obviously all your group 1s have 1 electron in the outer shell, all your group 2s have 2, etc, etc. So obviously you need to be aware of that. Again, some of this stuff you probably would have seen at GCSE. So really important though is that elements in the same group have similar properties. Okay, so for example, group 1 elements react with water with increase in vigor as we go down the group. And you might have seen this actually in the practical. The teacher might have shown you this, where they put some, say, sodium in or potassium, quite fiery, into the water, into a big kind of glass bowl of water with a screen in front. And it goes bang, and it really bright. It burns. Some of them, for example, sodium burns with an orange flame. You get this nice orange flame that's produced. And it might whiz around in the water as well. So as you go down that group, they're becoming increasingly more reactive. They're part of the same family, I suppose, family of elements. So periods, you might see, obviously, mention the terms periods. These are obviously the rows in the periodic table. And obviously elements in the same period have the same number of electron shells. So that's really important. They might have different subshells that make that up, but they've got the same number of shells. And obviously these elements, obviously we know, are known as your S blocks. These, remember, are known as your P blocks and your D blocks. And obviously you just need to be aware that the ones at the bottom there are known as your F block elements as well. So really important that you kind of understand this terminology, because we're going to be using it quite a bit later on as well. Okay, and have been actually, to be honest. So, okay, so let's kind of look into this a little bit further and try and apply something to it. Now, here we're going to look at atomic radii. So, radii is obviously what a radius is. So it's obviously the size of something. So, as we go across period 3, okay, remember a period is going along the periodic table, then the atomic radius actually decreases as we go across there. So remember, they all have the same number of electron shells, all these elements here, okay? So when we plot the graph of atomic radius for these period 3 elements, we get something which you can see in the bottom right-hand screen. And the reason why these actually decrease just slightly, as we go across this period, is actually there's an increased charge because there's an increase in number of protons. So remember, as we go across a period, we're just adding one more proton, or one more proton. Each element has one more proton than the previous one. But the critical thing here is that the number of shells isn't changing. So what this does, it pulls the outer shell of the electrons a little bit closer to the nucleus. It's just tightening that kind of atom up, or the size of the atom, a little bit more. And obviously the extra electrons the elements gain across the period go into the same shell, and so the shielding effect is similar. Okay, so we're not adding another shell in there which is significantly further away from the nucleus. They're all going into a very similar shell. So that's why the kind of atomic radius shrinks as we go across there. Okay. Now, obviously this, as we go down groups though, so if we look rather than across a period, we go down groups, then the atomic radius actually increases going down the group. And this is because you've got an extra electron shell for each element down the group. So as you go down, you've got another shell, another shell, another shell, and that shell is obviously further away from the nucleus, and so therefore obviously the attractive force is weaker, and so therefore the atom gets bigger as you go down a group. Okay, so let's have a look at some first ionizations across periods instead. So remember, we looked at first ionization in a group, so we're going to look at it in a period here instead. So similar thing. So ionization energy increases as we go across a period, and you can probably guess why, I would like to think. So like we said before, as you go across the period, there's an increase in number of protons in the nucleus. Okay, so obviously there's a greater nuclear attraction as you go across a period. So the general trend is that it increases over that time period. Shielding is quite similar, so obviously the distance from the nucleus marginally decreases. There's not that much of a difference, but the shielding is similar in this sense. We're not adding extra shells, and so therefore more energy is required to remove the outer electron, and so therefore the ionization increases generally across a period. Okay, and that's really important when we say generally. But as you can see, and obviously this is similar for the second period as well, But as you can see, there's a few blips in there, okay, and we need to try and explain why we have these blips in the trend, as you can see there. So, a decrease at aluminium, and if you look on the graph here, you can see aluminium is there, so right there. So there's a slight decrease there, and this is actually evidence for atoms having subshells. So remember when we looked at ionization down a group, and that was proof that we had a shell structure, so we had obviously different amounts of energy required to remove the electrons. Well, as we go across a period, this provides evidence of these subshells. So it's not just good enough to say, well, these exist. We need to prove it. We need to say, well, how do we know they exist? And this is the evidence for that. So the outermost electron in aluminium sits in a higher energy subshell, slightly further from the nucleus than the outer electron in magnesium, effectively. So if you look at magnesium, there we are. So magnesium is 1s2, 2s2, 2p6, 3s2. So that's magnesium there. And we want to try and remove that electron from this. But for aluminium, it's basically got that extra electron in that p subshell, and that's slightly higher in energy than the s subshell. So remember the diagram that we put up earlier on. That slight higher in energy makes it a little bit easier to remove that electron than it would be from the s subshell, because it's marginally further away from the nucleus. So that's why you've got this slight dip for aluminium. Okay, so that's in the 3p subshell. So magnesium is obviously in the 3s. And this is obviously a similar trend for period 2 as well. So if we pull up that diagram, and let's have a look. So this is a different one for sulfur in this case. Okay, so we've got this decrease at sulfur. And the reason why we have a slight decrease here is that these ones, remember, the first two ones here, so this is your S subshell. This enters the P. Remember, P, you can have 6 electrons in the P subshell. So that's 1, 2, 3, 4, 5, 6, which are these ones here. So these are actually all in the same subshell, as you can see there. That's this one here. So with phosphorus and sulfur, these both have outer electrons in the 3p orbital. So the shielding isn't actually any different here because they're all in the same orbitals. There's no difference there at all. So there must be something else at play here that's actually causing the energy required to remove an electron from sulfur to be slightly lower, not much lower, than it is for phosphorus. And it boils down to that bus analogy that I mentioned before about electrons not liking to be near each other. So when you're removing it from sulfur, sulfur has this configuration in its 3p subshell. And here you've got 2 electrons sitting in the same orbital, which they don't really want to do anyway. They don't want to be there unless they absolutely have to. So when you're removing an electron from an orbital that already has an electron in there, it's quite happy to be removed. It's, there's repulsion here. You've got electron repulsion between these elements here. So these obviously repel each other, and so therefore less energy is needed to remove an electron from an orbital with 2 in than a one with 1 in, like we had with phosphorus. Okay, so that's going to be, quite an important concept, because this is what we call electron repulsion, and we need to be aware of that in terms of the trends that we see, in particular for obviously elements like this. And obviously this is a similar trend for period 2 as well. There's no difference there. So it's really important that you're able to kind of describe this and use these keywords like electron repulsion and repelling and orbitals, suborbitals, p orbitals, s orbitals, all these words. This is what they're looking for in the exam, and you make sure you've got to include them terms in there. So, and that's it. That's topic 1 for the atomic structure. Quite a lot of information there. It's quite a tough start, really. There's a lot of new stuff there. And hopefully it's bridged a little bit from GCSE as well and kind of just extended it, kind of A-leveled it, I suppose. So hopefully, that was useful. As I say, all these slides are available to purchase. If you click on the link in the TES shop, you can get a hold of them there. They're great value for money. Like I say, these ones are clubbed together with other topics as well. So hopefully it's useful. And that's it. Bye bye.